findings on the moon that have been reported. We have a lot to cover. I'll introduce our participants. They'll give brief opening remarks, and then we'll open it up for questions. Starting off will be Jim Green, the Director, Planetary Science Division, the Science Mission Directorate at NASA headquarters in Washington. Carly Peters, Principal Investigator for the Moon Mineralogy Mapper, or otherwise known as MCube, from Brown University. Rob Green, Project Instrument Scientist for MCube at NASA's JPL in Pasadena, California. Roger Clark, Team Member, Cassini Spacecraft Visual and Infrared Mapping Spectrometer and MCube Co-Investigator from the U.S. Geological Survey in Denver. And Jessica Sunshine, Deputy Principal Investigator for NASA's Deep Impact Extended Mission and MCube Co-Investigator, Department of Astronomy, University of Maryland in College Park. Let's get started. I'll turn it over to Jim.
Thank you very much, Dwayne. We're going to start today by putting the water story in context, a historical perspective, if you will. And to do that, we'll start at the beginning. The generally accepted theory of the origin of the moon goes like this. About 4.5 billion years ago, an object, perhaps the size of Mars, slammed into the Earth. And as these two objects reformed and the moon coalesced from that collision, it lost most of its volatiles, and that includes water. This theory is very consistent with the known observations of the Earth-Moon system that we have today. And in fact, it's quite consistent with the results from the Apollo astronauts that brought back over 840 pounds of rock from the moon over several missions in the late 60s and 70s. And in fact, we have those rocks, we've made those measurements, and on the average, there's about 50 parts per million of water in the lunar rocks. So what does that mean? If we were to extract all the water in the Apollo rocks, it would fill this tablespoon. In other words, the moon, as we've known it, based on our theories and based on the observations from Apollo, is a very, very dry object. The next part of our story is Lunar Prospector. Launched in the late 90s, Lunar Prospector, with an array of instruments, observed the moon in its polar orbit and found something startling. And that startling measurement was from the neutron spectrometer. What it was measuring were neutrons that were being emitted by the moon, caused by cosmic rays that penetrate its surface, generating these neutrons. But over permanently shadowed areas in the northern and southern hemisphere, the neutron flux dropped significantly. Now, one of the absorbers of neutrons has been known for some time, and it's water. So therefore, at the end of the 90s, and as we move into this new era, the generally thinking idea is that the moon is bone dry, but there may be water at some amount in these permanently shadowed regions in the North and South Pole. Well, what we're going to talk about today is truly a major advancement in our knowledge of the water content on the surface of the moon. 3 papers will be published in Science today that will illustrate an enhanced knowledge of the percentage of water that exists all over the moon, and not just in these permanently shadowed craters. In fact, the observations of today, we will not be able to comment on how much water is in those craters because we can only measure from these instruments the light that comes back from the moon. These new observations that will be reported here are from 3 major instruments. The instruments are the Moon Mineralogy Mapper, or MCubed. This is on Chandrayaan-1. Second instrument is the Visual and Infrared Mapping Spectrometer, or VIMS, on the Cassini mission. The third instrument is the High Resolution Infrared Imaging Spectrometer, or HRIIS, on the Deep Impact, which has gone into an extended mission and is referred to as many as epoxy, but it's the same spacecraft. Now, these high-resolution imaging spectrometers make it possible to map the lunar hydrogen content on the surface as never before possible. The measurements from all three instruments, I think you'll find by the end of today's conference, as being quite clear, were critical in confirming the findings that we're going to talk about today. Now, before we get started, I want to take this time to especially thank the Indian Space Research Organization, ISRO, that is the Indian Space Agency, for the partnership and collaboration with NASA that has made Chandrayaan and M-Cube possible. ISRO shares in the credit the observations and findings that we will discuss today. We are delighted that they are here, represented by Mr. Karnik from ISRO. Welcome. And without further ado, I'd like to turn it over now to Dr. Carly Peters, M-Cube Principal Scientist.
Thank you, Jim. Well, the moon continues to surprise us. And that's the message that I hope you will take home with you today. Widespread water has been detected on the surface of the moon. You have to think outside of the box on this. This is not what any of us expected a decade ago, but widespread water has been detected on the surface of the moon. So if we could have my first chart. I'm going to be talking about the M-Cube results and giving you a quick overview of what they are and a few highlights of what we've seen. This particular figure summarizes the observations acquired during what we call the first optical period of the Chandrayaan operation for the near side of the moon, the part of the moon that you're all familiar with when you go outside and look at the moon. It illustrates the distribution of several highly diagnostic spectral properties. The blue tones in this particular image illustrate where we have observed with the M-Cube geometry the distribution of the surface, on the surface of H2O and OH, water and hydroxyl. The green and red tones and the variations amongst them are, in this particular image, are designed to illustrate the location of a variety of mineral species across the surface of the moon, which is what the instrument was specifically designed to detect and map. We will not spend much time on that part. We'll concentrate on the detection of water near the high latitudes in this particular image. Let's go on to my next chart, because what I need to explain to you right from the beginning is how we detect and why we are so certain that what we're looking at is water and hydroxyl on the moon. We use a variety of spectrometers, the one on M-Cube and the one on the other two instruments that you'll be hearing about, to look at radiation that's reflected from the surface and measured with these various detectors. It's measured as a function of brightness, as a function of wavelength or color. In this particular chart over on the left is, you can see right up at the top where the visible part of the spectrum occurs, where your eyes can tell the color of the surface. Moving to longer wavelengths or into the near infrared, you see a variety of highly diagnostic features that are due to the various minerals on the surface. Highlighted over on the left-hand part of this chart is the blow-up of the area that's uniquely diagnostic of OH and water on the surface of the moon. And I've identified in this particular figure where you see the diagnostic absorptions of OH and H2O, as well as the solid form of ice on the surface of the moon. And we'll all be coming back to this fingerprint, this highly diagnostic signature of detecting water on the surface of the moon. Okay, let's move on to my next chart. What's shown here is, again, a summary of the M-Cube data. Shown on the left, labeled albedo, is essentially the brightness of the surface of the moon as you would go out and look at it on a lovely moonlit night. That gives you an orientation that you should be quite familiar with. Shown on the right is the distribution of the signature of OH and H2O that M-Cube has detected. You can